Okay, welcome. Thank you for coming. And for all those of you watching this as a recorded video, thank you for watching it. This is the week 5 webinar of the online statistics class. And let me tell you the plan today. As always, I'll always happy to answer questions. And then we're going to get into sampling distributions. Okay, so last week we talked about the normal distribution. This week we'll understand why. And we're going to be looking at sampling distributions. And I don't know if I've mentioned too many times, but statistics is all about taking samples and then seeing what you get from them. And that's why we're going to be looking at sampling distributions. We'll look at unbiased and biased estimators. Then we're going to look at the most important theorem of all of statistics. It's got three main pieces. The first is a central limit theorem for means. And then we'll get into the central limit theorem for proportions. And then we'll get into the central limit theorem for sums. So this is the webinar pretty much all about the central limit theorem. That's what it's all about. I also wanted to give you some reminders, and that is this is an odd week, so there's no exam, but there is a project due. Okay, and in fact, by the way, the two projects are due on odd weeks because there's no reason to make you do both at once in the same week. So the project is due on Sunday. If you want me to read your draft, before you turn it in, send me an email with your project, your draft, and that has to be sent by Thursday at 8 a.m. If not, then I won't read it. Okay, so that's an absolute, you must send it by then if you want to send me your project for suggestions. And I will let you know it makes a huge difference because if there are issues, I'll let you know the issues and you can fix them and then you have a much better project. Whereas if there's issues and you don't send it to me, I don't know about it, I can't help you. And then you're going to lose points because of the issues. And you won't fix them because you don't even know to fix them because you didn't send them to me. So that's a big, big thing. I want to also let you know that Hector is definitely around this week to help out with the project. And again, you can go to his hours and talk about the project, and he'll help you out with it too. So again, the project is kind of the big central focus of the week. I mean, there is the central limit theorem, but the project is the biggie, and make sure you get that in. And I want to triply remind you, it's not okay to turn it in without a partner. It's pretty much impossible to pass because it's a huge point deduction. So make sure that your partners are still around. So communicate with them. Okay. And then when you turn in the project, only one of you needs to turn it in. Make sure all of your names are on it. And just a reminder, make sure that you copy and paste the spreadsheet, the important parts of the spreadsheet onto the project, and also copy and paste the charts, the statistical charts onto your project so that I can grade it. Okay, so those are all important. Any questions at all about the week? Any questions? Okay, and again, I always be looking at the chat, so feel free to put in the chat. And besides that, I'm about to ask you a question, and we'll see if you can tell me. It's going to take a minute. So here's your question. I figure you might know what's the big thing happening on Sunday. Yeah, Super Bowl. So here's what I want you to do. I want you to go online, look up 3 football players, find the mean and standard deviation of their ages. Okay, it shouldn't take more than a couple minutes. So you want to find the mean and standard deviation of their ages. Okay, and just let me know. And if you can't, if you just want to type in the 3 football players' ages, that's good enough. And then I'll get the mean and standard deviation for you, because that might be faster since we don't have too many people. And maybe actually you could do it too. That way we have a sample size that's a little bigger. So just find 3 football players Okay. And these are NFL players. And find their ages and type the ages in the chat box. Again, go online, favorite football player, how old is, and it'll tell you. Actually, if you put the type of person's name in, it shows you their date of birth, and their age for like any famous person that you put a name in. Let's see, you can do that because that's important. Because what we're looking at is we're looking at samples. And I know that sample size here is 3. That's just so we can do it fast. Normally, you do a lot more than 3. You do, over 30 is going to be our big thing, but 3 just so we can go quickly. And what we're going to want to do is really understand when you have a sample, what can you get from that sample? So hopefully you can put the chat box, the mean and standard deviation. I mean, sorry, the ages of 3 football players that you want to put in. NFL football players. And pop in the chat box. Shouldn't take too long. You just go online and ask. And if you don't know the 8 names of any of them, you can just go on to, some sports thing and type it in and give me names of 3 people from this team. So let's see if you can give me names of 3 football players from NFL. Here we go. Yeah, I don't need the names. I just want the ages. Sorry. Okay. So what we got, at least for this group, 43, 37, 34. Okay. And then, by the way, we can go to the calculator if you want very quickly. We can get into the one variable statistics calculator. Go to 43, comma, 37, comma, 34. And this will be a sample. So sample standard deviation, calculate. The mean is 38. The standard deviation is 4.5826. And I'm not sure if Hector you're doing it or not, but okay. So I think I'm going to go on and talk about, at least we have one set. So here we go, 29, 34, 37. And we get 33.3 and 4.0415. Okay, so what we have noticed is we have now 2 samples. We have 2 standard deviations. They're not the same. They're not the same mean. They're not the same standard deviation. They're definitely different from each other. And that's how it works. Because if you have a sample size of 3 and you research and find 3 football players, then someone else does the same thing, they're going to have different answers almost all the time. So if we want the population mean of all NFL football players, that would be much harder. Do you agree? Because I don't have the time to find a list of every football player in the NFL and get its mean and standard deviation. So typically, when you have a big population like that, you only can do a sample. And that's what we're going to be looking at. Okay. So the idea here is there is an X bar, which is the sample mean, and there is a mu, which is a population mean. We don't know the population mean. We don't know the population standard deviation. We could look it up. I'm not sure if anybody knows, but maybe. Let's see. What is the average age of NFL? Let's see. Tell us 26 years old. Okay, so we're gonna assume that Google got it right, and that's 26 years old. The standard deviation, we don't know. It's some other number. It might be, 8 years. Who knows? Okay. Any questions on that? Okay, so what you're going to do in the real world typically is you're going to do a sample, and you're going to use a sample to approximate the population. Okay, that's a big deal. And what we want to find out today is how good an estimate do you have? Okay, so notice, in fact, if you look at these X bars, 38 isn't anywhere close to 26 years old for a football player. So just got bad luck, right? Maybe it was biased, and 33 isn't that close either. So you're not going to get the exact population mean. What you want to do is you want to find out, well, maybe how far is it? So let's take a look at thinking about what's going on. Imagine taking every single sample of size 3 of ages of football players. Okay, and there'd be thousands and thousands, maybe millions of different samples you could do, okay, of size 3. Okay, then we can look at the sample mean of each of those samples, and that'll give you a whole lot of data values. This is all in theory. You never get every possible sample in practice, but at least you can imagine it. Okay? And imagine taking those data values and setting up a histogram with those values. Then you're going to have a shape of the histogram, which is the distribution. And the distribution of all possible sample means with the same sample size is called the sampling distribution of the sample means. Any questions on that? So I want to give you a heads up. There's going to be a lot of vocabulary and a lot of symbols today. And this vocabulary is important. This is called the sampling distribution. So it's the distribution of all possible sample means. Okay? Is a sampling distribution of the sample means. Okay? And one thing you might be interested in is if you think of all possible sample means and you write them out, and those are all numbers, and you take the average or the mean of those numbers, any guess what you get? If you took the sample mean for all possible samples of 3 football players, any guess what you get? Any thoughts? I don't see jumping in. Okay, it turns out if you take the population mean of all possible sample means, you actually get the true population mean of the original population. So if 26 really is that true population mean, that's what you would get. If you average 38 and 33.3 and the next one that you did and the next one and the next one and the next one, a million times later, average them all out, you'll actually get the population mean. Okay, now comes an interesting thing. We're talking about the population mean of all possible sample means. The population mean we use the letter mu for. Sample means we use the letter x bar for. So if you're looking at the population mean of all possible sample means, we use mu sub x bar. So mu with a subscript of x bar. Any questions on that? Any questions? Okay, similarly, if you have all these different sample means, you could find the standard deviation of all the sample means. Standard deviation will be sigma. and that would be sigma sub x bar. Any questions on these symbols? They're very important. We often call the sigma sub x bar the standard error. I think I'm going to boldface it because it's really important. So that's a standard error. It's a very, very important statistic, is the standard error. And in fact, I want to let you know, remember the project one, kind of one of the biggest statistics you have to do in the entire project one is a standard deviation. It turns out project two, it'll be the standard error. Project one, you're not going to be using what, we're talking about this week, but project two, you will. Okay, because this week isn't due until Sunday, and that's when the project's due. I wouldn't make you use this stuff for the project, but it will be used for project two, because that's like a long time from now, something like 6 weeks from now. So if we consider a collection of all possible sample means, okay, this is its own data set with a very, 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 very large sample size. Imagine taking samples of size 40 of people in America. Okay, and how many samples of size 40 are there? Here's a hint. My guess is you don't even know the name for this number because it's such a big number. It's much bigger than a billion or a trillion, by the way. Just give you an idea, gigantic. Okay, so there's so many of them. This is all theoretical because you can't actually get them all. But what you can do is you can theoretically think about them. Okay. So now we have, again, the sampling distribution is for a statistic for a sample size of size n is the distribution of all possible sample statistics from samples of size n. Okay, so we're looking at a statistic. One statistic that a very important statistic in this class is the mean, right? That's the sample mean. That's a biggie. What's another really important statistic besides the sample mean? You may not guess it, but it's the next most important statistic, maybe even just more important than the sample mean for this class or for statistics. No? Give you a moment. Don't see y'all jumping in. Okay. So the other really, really important one is when you happen to, instead of have a quantitative question, if you had a yes/no question, then it's a proportion that you're interested in. And a proportion, we have a yes/no question, but if the proportion is 0.8, 80% said yes, then that's a number. So then if you asked a bunch of groups, each group will have that like an 80% and a 75% and a 63% and a 23%, whatever they might be. And you have a lot of numbers, and you can take the mean of those numbers and the standard deviation of those numbers. So even for a yes/no question, you can have a sampling distribution for the proportion, and that will have a mean and a standard deviation. Any questions on this idea? And I do want to give you a big heads up. What we're talking about today, we're going to be using for pretty much everything we do for the rest of this class. So please ask questions if you have any, because it's really important. Okay, and there's a lot of language today. Not a lot of math. There's a little math, but there's a lot of language. Okay, so now comes a big definition that's really important when you're doing statistics, is a statistic is an unbiased estimator for a parameter if the mean of the sampling distribution for that statistic is equal to that parameter. Okay, this is kind of really abstract sounding, so my guess is you may not even know what I just said. So it's good to have some examples. Okay, one is the sample mean, and that's one we talked about. So if we looked at groups of 3 people, and we looked at all possible groups of 3 NFL players, and we looked at the sample means of all the groups, we took the mean of all the sample means, you actually will get the population mean. So the sample mean actually is an unbiased estimator, okay, for the population mean. Okay, here's another example. Let's suppose we wanted to find out what the average weight is of human beings in the United States of America. Okay? Human beings that right now are currently physically in the US. Let's suppose that you took a sample of, let's say, 10 human beings, and you look at the range of the weight of how heavy those 10 human beings are. So you look at the range, and if you remember, the range would be the heaviest. So the weight of the heaviest minus the weight of the lightest of those 10 people you asked or weighed. Do you think that's a good guess for the range of the weights of all human beings in the United States of America? What do you think? Do you think that'd be like a really good estimate, or do you think it'd be too small, or do you think it'd be too big? What do you think? Maybe put in the chat box what you think. Okay. So you're right that it isn't the same, but if you think about the range of those 10 people, okay, that means the big fat person minus the thin person versus the range of all Americans. That would be the fattest person in America minus the smallest person in America. Okay, the range of all Americans, now you're talking about this 400-pound person and this infant that was just born, way underweight, that might be 2.5 pounds. Okay, if you randomly grab 10 people in America, you're not going to find anybody like those people, or it's very, very unlikely. Does that make sense? Yeah, so you would not, so that the range you would get for the 10 people you asked is going to be too small. It's going to be much smaller than the range of all Americans. Is that clear? Okay, so you would never want to use the range of a sample as your estimate for the range of the population. So that would be a biased estimator. Any questions on that? Okay, the sample proportion is an unbiased estimator for the population proportion. Okay, so if you ask 10 people a survey question, a yes/no question, you look at their average, and you looked at every average of 10 people's yes/nos, a proportion, I mean, take the average of all the proportion of yes/nos of 10 people, you'll get the proportion of all Americans. So the sample proportion is also an unbiased estimator. Any questions on that? That's going to be very important in this class. So that means that the sample mean is your best guess for the population mean if you know nothing else. And the sample proportion is your best guess for the population proportion if you know nothing else. That make sense? Okay. I do want to note something, and I'm going to kind of say it quickly and not explain it at all. It turns out the sample standard deviation is very slightly biased. So it's not an unbiased estimator. It's just slightly biased, especially with a big sample size. It's like you might be off by like 1/1000th of a percent or something. So that turns out to be a biased estimator by a little bit. And the math is way too hard for me to explain. Even the idea is too hard to explain why it is. So this is the old trust me. Sound good? Okay, ready for the biggest theorem of this entire course? We're going to use this in a big way. And that's the central limit theorem. Okay, so the central limit theorem. So the idea is what you want to do is you want to say, well, if you take a sample and you want to think about all possible samples, so you want to look at the mean of all possible sample means, and you want to look at the standard deviation of all possible sample standard deviations. We want to say, what are those? And also, if you look at all possible sample means and you put them on a histogram, what's going to be the shape? Any guess what the shape might be? See if you can guess. What do you think the shape of the histogram will be if you looked at all possible sample means and you made a histogram out of it? What would its shape be? Any guess? Hope is you might be able to guess. Don't see you jumping in. Maybe you can't guess. I don't know. Okay, if you can't guess, let's go through it. So here is the central limit theorem. Okay, we look at the sampling distribution for sample means, where every sample size is n, some number n. Then we have the following. Mu sub x bar equals mu. So the mean of all possible sample means is the population mean. Here's a biggie. Okay, this is easy and everyone remembers this one because it's just, hey, the mean is the mean. The standard deviation, sigma sub x bar, the standard error, which is the standard deviation of all possible sample means, is not equal to the population standard deviation. It's equal to the population standard deviation divided by the square root of the sample size. Okay, and that is really important because if sigma sub x bar is really small, then if you randomly, did a sample, and you have a very small sigma sub x bar, that means it's very likely that your sample mean is going to be very close to the population mean because that's what the standard deviation tells you. It's how likely you are to be close to the population mean. Any questions on that? Okay. And dividing by square root of n makes a number smaller. So if n is 100, then you get sigma over the square root of 100, which is a sigma over 10. So then what you're doing is you're reducing that standard error from what the standard deviation originally was to 10 times less. And that means you have 10 times a better estimate than you had before. Any questions on that? Okay, now the second one is the following. If the population distribution is normal, or if the sample size is large, and in our class, our definition of large will be greater than 30. Where have you heard greater than 30 before in this class? Very important this week. Where have you heard greater than 30 before? Yeah, project one, you had to make sure your sample size was greater than 30, and that's the reason. And I told you when we first talked about it that I couldn't tell you then, but I'll tell you, eventually. Now we're here. So if we're greater than 30, then we know the sampling distribution for the mean is approximately normal. And as I mentioned last week, the normal distribution is by far the most important distribution of all distributions. And this is the reason. Because when you're doing a sample, then the sampling distribution is approximately normal. And statistics is all about doing samples. Any questions on that? And just note, 30 is not greater than 30. You need to be 31 or bigger for our class. Okay? There's complications that I can't talk about, when you need a little more, a little less. But in our class, we're going to stick to 30, greater than 30, because this is elementary statistics, and I want to make it easy. So it's just one answer. Got it? Any questions about the central limit theorem before I do an example? Okay, ready for an example? Okay, this is a very important example for your life. Okay, and here it is. Okay, and it's gonna be a three-part example. Here's the first part. Let's suppose you have $10,000. Okay, if you put it into the bank, what is the probability that you will end up losing money after 1 year? Okay, so what is the probability that X is less than zero? That means losing money, where X is the amount of money you made. And the hint is this is really easy. You don't even have to know any statistics. What's the probability of losing money if you drop money in your bank? What's that probability? Hint is it's easy. It won't take more than a second to type. I don't see y'all jumping in. If you put money in the bank, then a year later, you get your money back. Probability zero. You don't lose money. And if the bank goes bankrupt, by the way, I don't know if you know, but if you put it into Wells Fargo or Bank of America, whatever, and even if the bank goes bankrupt, you still get your money back because it's part of the United States. Okay, you may not allow, but that's the law. So there is 0% chance of losing money. Is that clear? Okay, so is this a good investment? It's safe, right? But here's a bigger question. What is the interest rate? How much money are you going to get on average? Which is how much money are you going to get back? How much money are you going to make? Okay, not zero actually. If you put money in the bank, there's an interest rate. I don't know if you ever look at your account every year, but I make a little bit of money. But the mean interest is probably about 0.3%. It's like very little. You do make a little tiny. Does that make sense? Any questions on that? Okay. So if you put $100 in, if you put $10,000 in, then you'll make like $30 out of that $10,000. But it's a 100% chance, a 0% chance of losing money. So are there any other ways, if you have this money and you don't need it this year, you want to just, make money out of it. What's another thing you can do besides stick it in the bank? Yeah, you can invest. You can invest. So here's the next question. Let's suppose you put your $10,000 into a randomly selected stock. And over the last several years, the mean was 9%, and the standard deviation was about 20%. Okay, stock market goes up and down and up and down. My guess is you probably know that, right? Okay, we're going to assume the stock returns are normally distributed. What's the probability you're going to end up losing money? Well, what's the probability that X is less than zero? The mean is 9, standard deviation is 20. So if I go back to my calculator, we have a normal probability. The mean is 9. The standard deviation is 20. We want the probability of losing money, which means we're less than 0. Because that's what losing money means, right? Any questions on this so far? And I hit calculate. Okay, my probability is about 0.33 rounded to 2 decimals. So there's about a 33% chance of losing money. Okay. Now, if this money is important to you and horrible things going to happen if you end up losing money, this may not be a very good investment. Do you agree? Yeah, you're going to make, on average, you're going to make 9% instead of a third of a percent or 0.3%. You're going to make 9%. That's much better, but you might lose money. Any questions on that? Okay, anyone, any idea of another choice of investment? I like to do this because, doesn't matter what your job is, hopefully you'll make money and you'll have money to invest and you're going to have to decide what to do with it. Any ideas? There's a lot of different choices, but I was going to go through one, but let's see if anyone guesses what I'm going to go through. Don't see guessing. Okay. All right. Let me give you another example. Okay. Let's suppose instead of just buying one randomly selected stock, you put your $10,000 into a Dow Jones index fund, which is 30 stocks. Okay. So you probably heard of the Dow Jones. And what that does is it invests in all 30 of them. Okay. Not 10,000 in all 30, but it divides 10,000 divided by 30 basically. And then and then you invest in all of them. Does that make sense? Now, what's the probability of losing money? Any questions on the question? Okay, we're going to assume that the Dow Jones is a representative sample, and we're going to assume that stocks are independent of each other, which may not be perfect. There are actually better things, but they're too complicated for me to do this class. I can only tell you so much about investing, but this is the idea. So our mean is still 9%. Okay. Sigma for all stocks is 20, but now we have a sample size of 30. Any questions on that? All right. So what we want to say, what is the distribution of not an individual stock, but what is the distribution of the average of 30 randomly selected stocks? Okay. The average is an X bar. That's a sample mean. Remember, tilde means has a distribution and n means normal. According to the central limit theorem, mu sub X bar is mu. Mu was 9. So mu sub X bar is also 9. And then according to the central limit theorem, sigma sub X bar is sigma over the square root of n. And sigma was 20. N is 30. So I take 20 over the square root of 30, and that is my standard error. Any questions on what this is? Any questions? Okay, and then I put this in a calculator. 9 I didn't need because 9 is still 9. But 20 over the square root of 30 is 3.651483717. Okay, it's a messy number. The important thing is notice that the standard error is like between 3 and 4, whereas in a single stock, our standard deviation was 20. So our standard error is much smaller. So now we can find the same idea, but now we're going to have a very different sigma sub X bar to put in. So now if I go to normal distribution, the standard deviation will be this 3.6514, etc. I want to find the probability. I still want to find out the probability of losing money, which is probability that x is less than 0. And I hit calculate. What do you notice now? This probability is very small. It's not 0, but it's about 0.007. Okay, so if you have money to invest, if you put it in the bank, you will not lose money. But your interest rate is tiny. If you invest in an index fund, and I'm going to tell you, it's a little complicated, but I'm going to tell you, if you do it over, several years for sure, then the probability of losing money is almost none, but you're getting 9% interest on your money. Okay. So for investment purposes, this is much better than putting in the bank. If you're going to be doing, especially long term. If you can do it for a month, that's a whole different thing. You get a big standard deviation. And if losing money is a disaster for you, don't do it. Don't throw it in the stock. Okay. But if you're going to be doing it over, years, then that's what you want to do. Okay. For example, for a retirement fund, if let's say you're 30 years old, then you're not going to retire for 35 years possibly. And each year is another one of these years if you put an index fund. And that standard error is tiny. So you are going to make much more money than if you just put it in a bank. And you can actually put it in, a 401 plan, 403B or whatever you want to call it, depending on what your job is. And you don't have to pay taxes on it even. It's awesome. Okay, so again, one of the things I try to do in this class is give you life skills that's going to help you for your life. This is a lifetime thing. Any questions on that? Okay. On the other hand, one of the things when you have a small standard deviation, you're not going to make a huge amount of money either. Okay. So yeah, it's not very risky, but you're going to make close to 9%. You're not going to make 40%. That's not going to happen. Does that make sense? Okay. Personally, I actually do two types. I have my kind of long term, I don't want to lose money and I want to make sure that I have an okay retirement. And I put that in index funds. But then I also do day trading. And that has huge standard deviations, it turns out. And we'll learn a little bit more about this later. You can actually use statistics and come up with ways of really making good money, on a day trading thing. But it's a long conversation. Even in this class, I don't have enough time for the whole course to tell you all the details of what I do, but just let you know that it can be done with a huge amount of learning. And then you can make good money. And I'm not the only one that's ever done that. I'll give you an example or two in a few weeks, 3 weeks, I think. Any questions on this? Okay, let's suppose that you want your standard error to be equal to 2. Okay, notice our standard deviation was about 3.65 or so. Do you see? That was our standard error. If you want the standard error to be 2, how big a sample size do you need? Okay, any questions on that so far? Okay, well, what you can do is just put it into the formula, which is 20 is our sigma. So I put 20 up on top. N, we don't know. That's what we want. So I'm dividing by the square root of n because that is our standard error formula. Went too far. There we go. Sigma over root n. And that I want it to be 2. Sometimes it helps to write 2 as 2 over 1. I know that sounds like more work than you want to, but it actually helps to see it. Because if 20 over root n is 2 over 1, I can cross multiply and say 20 times 1, which is 20, is 2 times root n. Then I could divide left and right by 2, and I get 10 equals the square root of n. And now I get rid of the square root by squaring both sides, and n is 100. So we need to have a sample size of size 100 if you want a standard error to be 2 instead of 3.65. Any questions on this idea? Okay, so often it's going to be very important to really understand how do you decide how big a sample size you need. Okay, whether it's for investment purposes or surveying or whatever you're doing, it's important. Okay, and I'll let you know it's something I'm going to want you to do in project 2. You get to do one of these calculations. Okay, so that was the central limit theorem for means. Very important, and it has lots and lots and lots of uses. Not just this example, but you can't imagine how many uses it has. So now we're going to say, what if instead we had a yes/no survey question? Now we're not talking about means anymore, because if you had, if you asked 40 people and 25 of them said yes, there's not a mean. It's 25 over 40 is your proportion. You see how that works? But we can still talk about the distribution for proportions. And here is a central limit theorem for proportions. I'm going to do this so we can put it in one page. There we go. And here it is. Let P be the population proportion. And just to let you know, for sample proportions, I've said this before, but now it really gets important because we have all these symbols. We put a P with a hat on top of it, and that's P hat. Now, if you're typing it in, like on your exam, you can type PHAT and I'll be okay with that. Okay, if you're doing it in a project, you can learn how to do the hat, but it takes some learning. But for a project, you get help and lots of time. For an exam, it's a whole different thing. So just let you know, PHAT is fine for the sample proportion. Okay, whereas P is the population proportion. We don't use Greek letters because the Greek for P is pi, and that confuses everyone. So we use P. Okay, and just note Q is 1 minus P. So if P is the probability of someone saying yes to the survey question, Q is the probability of someone saying no to the survey question. That makes sense? Okay. So here's number 1. The sampling distribution for sample proportions for samples of size n has mu sub p hat equals p. Okay, and we actually said that a little while ago because I mentioned that the sample proportion is an unbiased estimator. And that's what that means, is it means that if you take the mean of all possible sample proportions, you get the population proportion. Any questions on that? Okay, and then sigma sub p hat is equal to the square root of pq over n. And remember, P is a proportion of yeses, Q is a proportion of nos, N is the sample size. Okay, one thing to note is we're in a square root and we still have N on the bottom, so we have a square root of N on the bottom, just like we had before. So if you multiply your sample size by a factor of 9, then you're going to decrease the standard error by a factor of 3. Okay, because 1 over root 9 is 1 over 3. Any questions on this idea? Okay. Now comes something that a lot of people have trouble with. It's actually easy, but people have trouble. Okay, first thing, if N times P. That's the sample size times the proportion of yeses, which is also the number of yeses, or the predicted number of yeses. And N times Q, which is the sample size times the proportion of no's, which is the predicted number of no's. And if both of those are larger than 5, then the sampling distribution is approximately normal. Okay. I will let you know that so many people ignore this, and so many people lose points on their exams and everything else because they ignored this. Okay. If your survey is a yes/no survey question, you're not looking for a sample of size greater than 30. You're looking for a predicted number of yeses and a predicted number of no's, both bigger than 5. Got it? You can't even imagine how many people make that mistake. So here's what I want you to do in the chat box right now. I want you to type this in. I want you to give me a promise. For a yes/no answer, I will not use the number 30 to see if the sample size is large enough. Type that in the chat box. Okay. And by the way, if you're watching this as a recorded video, write that down on a piece of paper to yourself. I want you to make this promise because it's a mistake a lot of people make, and maybe if you promise me you won't, then maybe you won't make that mistake. So type that in the chat box. Give you a moment because it's so important. So if you have a quantitative survey question, you need a sample size bigger than 30. If you have a yes/no survey question, then you have to have the expected number of yeses and the expected number of no's both bigger than 5. So type this in the chat box, and I'll give you time. Okay? Good, good. So you made a promise. Don't go back on your promise. Okay, you do, you will lose a lot of points on your test. And by the way, if you didn't write it down on paper and you're watching this, then I'll still take a lot of points if you don't do it right. But I do everything I can to make sure you do well. And this is one of the things, maybe this will help. Okay, so here is an example. All right. And this was one thing I like to do, and hopefully you realize this, but usually, within a couple days before I give a webinar, I look at the news and I see what I can do and see what it said. And here I read this news article. Okay. And here's a question I have for you, which is based on the news article. Do most Americans think it's a good idea to use weight loss drugs for US adults who want to tackle obesity or similar conditions? So that's like Ozempic. Okay, Ozempic. So there's a few different drugs, but that's one of them. So have you heard about these drugs that will help you reduce your weight? Okay. Oh, I have a typo here. There we go. Yeah, so you've heard of it. So they did a survey, and the Associated Press, okay, the Nork Center of Public Affairs Research. I always like to give the report. They did a sample size of 1,447 people. Remember, these are all Americans. We have hundreds of millions of Americans. They only asked 1,447. Do you think they asked enough? What do you think? Think that was enough people to ask? What's your thoughts? Or do you think they needed to ask more, which costs money, by the way, because you got to pay people to do the surveys? I don't see jumping in. What do you think? Did they ask enough people? Okay, let's see jumping, we'll see. Okay. So this poll found that 54% of the respondents said it's a good idea to use weight loss drugs for US adults who want to tackle obesity or similar conditions. Okay. Is that most Americans? Is that the majority? Any thoughts? 54% of the respondents said it was a good idea. So can they say that most Americans think so? It's a good idea. I don't see you jumping in, so let's do some more work and find out. Okay. And by the way, they used online and telephone interviews using landlines to conduct the survey. So here is a question we could say. Okay. If it's not most Americans, by the way, the largest number to be not most is exactly 50%. Does that make sense? Because the definition of the majority is over 50%. So if 50% of all Americans think it's a good idea to use weight loss drugs for the US adults who want to tackle obesity or similar conditions, what is the probability that of randomly selected 1,147 Americans, at most, okay? Oh, sorry, that should be at least. That was my mistake. At least 54% of them think it's a good idea to use weight loss drugs for US adults who want to tackle obesity or similar conditions. So let's find this probability. So first thing we can say, what is a sampling distribution? Well, NP, if we're assuming 50% think it's a good idea, then NP is 1,147 times 0.5. Okay. And even if you don't want to use a calculator, you don't want to do it in your head, I think you all know that if you take half of 1,147, you get something bigger than 5. I hope you all know that, right? And NQ is going to be 1,147 times 1 minus 0.5. And 1 minus 0.5 is also 0.5, just coincidentally, by the way. That won't always be true for examples, but this one does. And that is obviously that's the same number. It's much bigger than 5, right? Half of 1,000 is 500. It's even bigger than that. Any questions on that so far? Okay, so then what we're going to do is we're going to use the central limit theorem. And that says that p hat has a normal distribution. That's p hat tilde n. And we're assuming that the population proportion is 50%. So that means sigma sub p, mu sub p hat is also 50% or 0.5. Sigma sub p hat is this messy, the square root of pq over n, which is square root of 0.5 times 1 minus 0.5, which happens to be 0.5, over 1147. All right. That is normal with mean 0.5, and I popped that in the calculator, and I got 0.01476. Any questions on that? Anyone lost? There's a lot of details today. Just one chapter. Doesn't make it easy, though. Okay, so if we want to find out what is the probability that at least 54% think so, then I'm going to go to my calculator. We want greater than 0.54. Our mean was 0.5. Our standard deviation was this 0.01476. And our probability is actually really small. 0.00336. Any questions? Any questions on this idea? Okay, so this is the probability that if 50% of all Americans, okay, think it a good idea to use weight loss drugs for the US adults who want to tackle obesity or similar conditions. And if they surveyed 1,147 randomly selected Americans, then at least 54% of them, okay, at least 54% of them, and then I just copy and paste, think that it's a good idea to use weight loss drugs for US adults who want to tackle obesity or similar conditions. Okay, that's a tiny probability, right? When you have a really small probability, you say maybe something's wrong. What was the assumption we used? What's the main assumption we had? You see it? Okay, our main assumption was that only 50% of all Americans think it was a good idea to use the weight loss drugs. Okay, so now we say, well, that's probably wrong. It's probably bigger than that. So we're going to probably say the majority. Okay, more than 50%. Any questions on this idea? I want to let you know this is the most important idea of all statistics, is to be able to come up with these kind of conclusions. We're going to have multiple chapters on all the details of what I just did. We have all kinds of language behind what we did too. But I wanted to give you an example that is important. Any questions at all on this? Okay. So it turns out when you're thinking about publishing papers, this is what they have to do. Okay, so last thing is central limit theorem for sums. All right, so now sometimes you're more interested in the sum than the mean. Can you think of when you might be interested? Remember, the mean is the average and the sum is the total. Can you think of when you'd be more interested in the total than the average? Can you think of examples? Real life examples? Any ideas? Yeah, I don't see jumping in, so I'll let you know. Business. Okay, so if you own a business where you sell stuff, it's much less important how much the average person spends, and much more important, how much total money you make. Do you agree? If you own the business, you care about how much money you made at the end of the day, not what was the average amount of money people spent. Do you agree? Because you just want to make money. So that's that. There's other examples, but that is the most important of all examples. Okay, there's other really important ones too. Okay, so here it is. The sampling distribution for sample sums from samples of size n has, now we're going to say mu sub, you may not have seen this before. This is a summation sign. It means add them up. Sigma x equals n times mu. And sigma sub sigma x. And by the way, this is capital Greek sigma. This is lowercase Greek sigma. So it's a little confusing. Sorry about that. Don't shoot the messenger. I just use what everyone in the world uses. Okay, so sigma sub capital sigma, lowercase sigma sub capital sigma x is equal to lowercase sigma times root n. Okay, that's just the way it is. Okay, if the population's distribution is normal and if the sample size is large, greater than 30, then the sampling distribution for sums is also normal. So it turns out to test normality for sums, it's the same as for means. Just want to make sure you have a bigger than 30 sample size. Proportions is a whole different thing. Okay, another way of writing this down is this capital sigma, or the total, is normally distributed with mean n times mu and standard deviation sigma times root n. Any questions on that? Okay, so here's another example. Suppose the average customer at a restaurant spends $33.23 and the standard deviation is $9.22. If 65 customers eat at the restaurant today, what is the probability that our total revenue for the restaurant will be less than $2,000? And then what is the first quartile for the total revenue for a day? Any questions on the question? See how important this is for business? Because you care about your total revenue. You gotta make sure if you're the manager of this restaurant, then you gotta make money. And it's the total amount of money that matters, not the individuals. Okay, so then we go ahead and use the central limit theorem. So again, remember sigma. So the sum or the total is normally distributed. We have n mu for the mean and sigma times root n for the standard deviation. Here n we had 65 customers. So n is 65. They averaged $33.23. So we're going to multiply by 33.23. Standard deviation is $9.22. So we take 9.22 and then we have to multiply by the square root of n, or the square root of 65. Any questions on that so far? Okay, so now I popped that in the calculator and I got 2,145 and 74.334. Just calculation. Any questions on any of this? Okay. So we want the probability the total revenue be less than 2,000. Okay, so again, what we need to do is we need to go to the calculator. We want less than 2,000. Our mean will be 2145. Our standard deviation will be 74.334. Probability, we don't know. That's what we want. So we leave that one blank. And hit calculate. And you get about a 2.55% chance. Or 0.0255. Any questions on the probability? Okay, then we also want the first quartile. So to get the first quartile, what do we have to change here to get the first quartile? In a calculator, what do we need? We want the first quartile, Q1. So what do we need? What goes in here? What do you have to type in? Because it's very important that you know how to do it. Just watching me and not knowing how to do it doesn't help at all. So if you want the first quartile, we've done this before, last week. Do you remember? Not with the same numbers, but same idea. I don't see y'all jumping in. Okay, if you remember, that's when the first quartile means there's a 25% chance of being less than that number. 25% chance, that's a probability. And that is 0.25 as a probability of being less than. So we do less than. That number is what we want. We don't know what it is, so that's when we leave blank. Any questions on that? And I hit calculate. And that is, let's go 2 decimals because that gives you dollars and cents. $2,094.86. Right, 209,486. Yes, I remembered it right. Any questions? Any questions on this idea? Any questions? Hopefully you see how important this kind of stuff is. And by the way, for the rest of this class after this week especially, then that's all we do is applications. Okay? Whereas today there's a lot of theory, but we did some applications at least. Any questions on that? Okay. If there's no questions, then the secret word is normal. Because the central limit theorem says that if you have a large enough sample size, then the sampling distribution, whether it's for means, for sums, for proportions, is approximately normal. So normal is a good word for the secret word. So that is pretty much everything I needed. I don't want to, be too brutal because remember you have your project due this week. That's gonna be what you're probably going to spend most of your time this week on. That it's not a short thing. So make sure that you put in time, get help when you need it. Again, I'm here to help. Hector's around to help, so are the tutors. Make sure you work together with your partners so that, we can make this work for you. So I think I'm going to call it recorded and we stop the recording. So thanks a lot for coming and for watching.